All right, 6.8, we're going to talk about sequences and summation notation. I'll say the last couple sections in this chapter are really, they're to help prepare you for calculus, but they do relate to functions. 6.9 is about integration. In calculus, you're going to learn about limits, derivatives, and integrals. In other words, taking limits, integrating, and differentiating, right? So we're going to talk about integrating in 6.9. In order to understand integration, you have to understand a little bit about summation notation, and in order to understand summation notation, you have to understand about sequences. Now, the good news is that this all ties into our study of functions because sequences are just a special kind of function, okay? So as far as our study of functions is concerned, we've still only scratched the surface. There's a lot that we could study about functions and how they behave. What I want to point out for now is that all of the functions we've looked at have had domains and ranges that were some interval of real numbers. But we could have functions whose domains and ranges are all kinds of sets. For example, we could have functions that map from R2 to R3 instead of from R to R, right? So like this one, it takes an ordered pair and maps it to an ordered triple. It's kind of fun to work with these things. For example, what is f of negative 3, 7? Well, f of negative 3, 7, if I'm using this as my function f of negative 3, 7, I'm going to plug in negative 3 for x and 7 for y. So I'm going to get negative 3 squared. Then I'm going to get 7 squared. And then I'm going to get negative 3 plus 2 times 7, right? So that works out to 9, 49, and 14 minus 3 is 11, right? So that is the output value when the input value is negative 3, 7. So we get this ordered triple as our output. Anyway, so we could talk about functions like this. In trig, you probably looked at parametric functions a little bit. Parametric functions are functions of the form f from r to r squared, or from r to r cubed sometimes. But anyway, so you've been exposed to these kinds of functions before, maybe not using this exact kind of notation, but you've probably seen them a little bit, and you'll see them again in calculus, right? So I'm not going to spend a ton of time talking about these kinds of functions, but I do want to talk about sequences. A sequence is a function whose domain is the set of natural numbers n. The range could be, whatever set, but the domain, the input values are going to be natural numbers only. Okay, so remember the natural numbers are the positive whole numbers 1, 2, 3, 4, 5, 6, and so forth. For example, f of x equals 3x plus 1, x in n would be a sequence. Right? That's a sequence. Now, if we list out all of the function values of f, then we get this following set of numbers, right? If we plug in 1 for x, we get 3 times 1 plus 1 is 4, right? If we plug in 2, we get 3 times 2 is 6, plus 1 is 7. If we plug in 3, we get 10. If we plug in 4, we get 13, and so forth, right? So if we list off all of the function values, we get this set of numbers. For that reason, it's common to write sequences as sets rather than in function notation, right? So instead of writing f of x equals 3x plus 1, where x is a natural number, we could just write the set of all numbers of the form 3k plus 1, where k is a natural number. But even more commonly, we would write sequences this way. We usually write sequences this way, right? So the set of all 3k plus 1 starting with k equals 1 and, going on forever and ever, right? That's how we would write that sequence. The function values themselves are called the terms of the sequence. Now, this sequence right here, it's a sequence of numbers that's generated by this rule. But a sequence of numbers doesn't have to be generated by any particular rule. It could just be a random string of numbers like this, right? This would be a sequence. But most of the sequences that we're interested in are generated by some kind of rule. So here's a famous one, the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21. If you're wondering what the pattern is, you get the next term in the sequence by adding the previous two terms, right? So 1 plus 1 is 2. 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, and so forth. So so that's a sequence that's generated by a rule, right? Here's another sequence generated by a rule. This one's even more straightforward because we're telling you the rule is going to be 2 to the k power minus 1. We're going to start with k equals 1, and then we're going to go on and on, right, forever. So starting at k equals 1, 2 to the first power is 2, and 2 minus 1 is 1. Then we would plug in 2. 2 squared is 4, 4 minus 1 is 3. Then we would plug in 3. 2 cubed is 8, and 8 minus 1 is 7. And then we could plug in 4, right? 2 to the fourth is 16, and 16 minus 1 is 15, and so forth. I think the next one would be 31, and then 63, and on and on. Okay? So these are the kinds of sequences that we're going to look at in a little bit more detail. These sequences that are generated by some rule like this. So example 1 says, write the first 5 terms of each of the following sequences. So for part A here, if we wanted to write down the first 5 terms, we would start off plugging in 1. 1 squared plus 1 is 2. Plug in 2. 2 squared plus 1 is 5. Plug in 3. 3 squared plus 1 is 10. And then we would get 17. And then at 5, we would get 26, right? And then this is going to keep going on and on forever, but we were only asked for the first 5 terms, so there they are. Okay, go ahead and give the video a pause and see if you can do parts B and C on your own. Okay, so you should be coming up with something like these lists. Well, you should be coming up with these exact lists as a matter of fact. Okay. So this is how sequence notation works. Okay. All right. So now, in calculus, you're going to spend some time classifying sequences as arithmetic or geometric or telescoping or whatever, right? They're all different kinds of sequences, and so you'll spend some time classifying them in calculus. We're not really going to get into all of those details, but one thing that I do want to kind of prep you for is that oftentimes in calculus, you're going to be interested in adding up the terms of a sequence. And to add up the terms of the sequence, we use summation notation. And here's how summation notation works. So let's say that you have this list of numbers, am plus am plus 1 plus am plus 2 and so forth, all the way up to some stopping point a sub n. If you wanted to signify that you're going to add those numbers up, then you could say that like this. We use a capital sigma. Sigma stands for sum. So it's a capital sigma starting at k equals m, so your subscript starts at m, and ending at k equals n. And then you're going to add up all of the terms of the form a sub k, right? Starting at m and ending at n. So you take turns plugging in m, and then m plus 1, and then m plus 2, and so forth, all the way until you get to n. Let me show you some specific examples, because this is kind of an abstract idea, and I think until you see some examples, it's a little confusing. But once you see an example, it's not bad. So let's say that we wanted to add up the following sums, right? So we want to add up k squared plus 1, k starting at 1 and ending at 3. So what we do is we take turns plugging in numbers for k, starting at 1, ending at 3, and of course we're only going to be plugging in whole numbers. So if we plug in 1, we get 1 squared plus 1. If we plug in 2, we get 2 squared plus 1. And we're going to add these up, right? And if we plug in 3, we get 3 squared plus 1. So it's going to be 1 squared plus 1, plus 2 squared plus 1, plus 3 squared plus 1. All right? So that's going to be 1 plus 1 plus 4 plus 1 plus 9 plus 1. And if you add all those up, you get what? 10, 15, 17. Okay, let me give you another example. Let's say that we want to add up k minus 5 over 3k, k starting at 2 and ending at 5. Okay, so we plug in 2 for k, and then we plug in 3 for k, then we plug in 4 for k, then we plug in 5 for k. And then we end at 5, right? So what are we going to get here? This is going to be negative 3 over 6 plus negative 2 over 9 plus negative 1 over 12 plus 0 over 15. Well, so that's just gone, right? But we've got to get a common denominator. Although, this is just negative 1/2, isn't it? So I guess, what would work? 36? 36 would work. Or you could just plug this into your, I'm just going to plug it into my calculator. I don't have time to sit here and mess with this. We got negative 1/2 minus 2/9 minus 1/12. That's negative 29/36. Whoops, 29/36. So there's that sum. Okay, part C. Part C is a little strange because you're going to start at 3 and you're going to end at 3. That means there's only going to be one term, right? You're going to plug in 3 for k, and that's it, right? So this is going to be 1/8 minus 1. That's negative 7/8. Okay, so again, kind of a strange one because you're starting and ending at 3. So you're not adding anything up, you're just plugging in 3. See if you can do part D on your own. Go ahead and give the video a pause and see if you can do part D. So I'm getting 320. Right? 2 times 2 plus 4 times 3 plus 8 times 4 plus 16 times 5 plus 32 times 6. Yeah, 320. Okay. So that's how that works. Let's do part E. So again, go ahead and give the video a pause and see if you can do this one on your own. This is kind of an interesting one. So the signs alternate, right? Because a negative to an even exponent is going to be positive, right? So anyway, so -1, positive 1/2, -1/3, positive 1/4, -1/5, right? That comes out to -47/60. Okay, and then part F, let's look at this one together. It's a little bit strange because the rule here doesn't even involve a k. So what does it mean to plug in k equals 1? Well, k can be whatever it wants to be. The output still needs to be 5, right? So we're gonna do this 8 times because we're gonna start with k equals 1, k equals 2, 3, 4, 5, 6, 7, and 8. So what you notice is that really this is just 8 times 5, right? 8 times 5, which is 40. Okay, so when you have just a constant term here, right, it doesn't change as k changes, but you still have to add it up 1, 2, 3, 4, 5, 6, 7, 8 times. Okay, we can also go backwards. If we're given a sum, we can rewrite it using summation notation. There are infinitely many ways to do this, so you're not going to get a unique solution. But here's how I would think about part A. I mean, it looks like one that we saw on the previous page, where the numerator is 1 less than the denominator, right? So it seems like if we call the numerator k, then the denominator has to be k plus 1, right? So, I'm thinking the rule is going to be k over k plus 1. And we want to add up a bunch of these things, starting with what? Well, we're going to start when k is 1, and we're going to end when k is 4. And there you go. So that would do the trick just nicely, right? When we plug in 1, we get 1/2. When we plug in 2, we get 2/3, and so forth. When we plug in 4, we get 4/5. But that's not the only way. That's not the only way you could have written it. You could have said, well, no, I want the denominator to be k. And if the denominator is k, then the numerator needs to be k minus 1. And if that's the case, we need to start k at 2, right? You start k at 2 and end k at 5. So this is going to generate the same sum as this does, right? And in fact, there are even more ways that you could write down this sum, but I'm not going to get into all of them. Either one of these would be a good solution. I think the top one is maybe a little bit more straightforward, though, so I'm going to circle that. See if you can do part B. Okay, so here's my solution. Looking at part B, it looks like I have perfect squares here, right? Like this is 2 squared, 3 squared, 4 squared, 5 squared, and so forth. If I want to think of this as the first term, so if I want to think of this as like the case that you get when k equals 1, then we would have to have k plus 1 squared, right? It would have to be k plus 1 squared if we're going to start at k equals 1. And then we would end at 1, 2, 3, 4, 5, 6, 7. Right? So when k equals 1, we get 1 plus 1 squared is 2. When k equals 2, we get 2 plus 1 squared is 9. When k equals 3, we get 3 plus 1 squared is 4 squared, which is 16. And when we get to 7, we're going to do 7 plus 1 squared, which is 8 squared, which is 64. So this looks good. Now maybe you thought, well, I just want to do, I noticed that they're perfect squares, so I'm just going to think of it as k squared. That would be fine, but then you need to start at 2, right? Because you need the first term to be 4, so you need to start k at 2, and then you need to end at k equals 8. But these two things are going to generate the same list of numbers as well. Part C is a little interesting. You might be able to recognize what's going on there. Give it a pause. See if you can write this down using summation notation. Okay, so here I go. The first thing that I notice is that the signs are alternating. Positive, negative, positive, negative, positive. we saw something that did that up here in part E. When you have a negative 1 to the k, that alternates, except that when it's negative 1 to the k, it starts negative, right? So it's negative, positive, negative, positive. We want to start positive, go positive, negative, positive, negative. So I think what will do the trick is if I do negative 1 to the k plus 1. That way, when k equals 1, I'm going to get a negative 1 squared, which is going to give me a positive. When k is 2, I'm going to get a negative 1 cubed, which is going to give me a negative, and so forth, right? So this part of it will take care of the fact that the signs are alternating. But then the numbers themselves, they go from 3 to 9 to 27 to 81 to 243. Notice that 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81, and 81 times 3 is 243. So I think what's happening is that I'm multiplying this by 3 to the k power, right? When k is 1, I get 3. When k is 2, I get 9. When k is 3, I get 27, and so forth. So that's that. 1, 2, 3, 4, 5. So we're going to stop at 5. Okay. So that should be a sigma. I'm sometimes very sloppy with the way that I write my sigmas, in case you couldn't tell, but there you go. It should be a sigma. Okay, so that's how summation notation works. Here's a particular sum that's going to be useful for us in the next section, so in 2.9, or sorry, in 6.9. This is going to be very useful, a very useful sum for us to know. So it turns out that if you add up the first n natural numbers, here's the summation notation for that. Well, it turns out that when you add up the first n natural numbers, you're going to get n times n plus 1 over 2. And here's a proof of that fact. So let's say that s sub n is this sum that we're looking for, 1 plus 2 plus 3 plus 4 all the way up to n. And let's say that we add the sum to itself, but in reverse order, right? So Sn is 1 plus 2 plus 3 and so forth all the way up to n. But you could do the addition backwards, n minus 1 and minus 2 all the way down to 1. And this should still be the same sum, right? Now, if you add that to itself, you're going to get 2 times the sum. But notice that here you get n plus 1. And here you would get 2 plus n minus 1 is n plus 1. And here you get 3 plus n minus 2, which is n plus 1. So each time you're getting n plus 1 all the way down to the end, right? You're just getting n plus 1. So you're just adding n plus 1 to itself a bunch of times. Well, how many times are you adding it to itself? Well, there were n numbers on the list, right? So you're multiplying n, or you're adding n plus 1 to itself n times. So in other words, that's just n times n plus 1. So 2 times the sum we're looking for is n times n plus 1. If that's true, then the sum itself, you can just divide through by 2. The sum itself is going to be n times n plus 1 divided by 2. And that's all there is to it. Okay, so let me show you this formula in action, right? So let's say that you wanted to add up the first 4 numbers. Of course, this is really easy to do by hand, but let's just use the formula to do it so that we can verify that it actually works, right? So the sum from k equals 1 to 4 of k is going to be n, which in this case n is 4, so it's going to be 4 times n plus 1 divided by 2. So that's 4 times 5 divided by 2. 4 times 5 is 20. 20 divided by 2 is 10. So we should get 10. Now we can verify that by actually doing the sum directly, right? If we actually just add this up, we would plug in 1, and then 2, and then 3, and then 4. And if you add those things up, you get 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10. Sure enough, right? So this gives us a little bit of, this convinces us, I guess, a little bit that the formula works. If in case the proof didn't do it for you, now you've seen a concrete example. You may think, well, but what good is that formula if we could just do this and that's a lot easier? Well, imagine that you didn't want to just add up 4 numbers. Imagine that you wanted to add up the first 300 numbers. So imagine doing 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, all the way up to 300. That would take you a long time. That would take you a long time just to punch it into your calculator. Even if you had a calculator to do the work for you, it would take a long time for the calculator to do it. Fortunately, we have this shortcut. We know that the sum of the first 300 natural numbers, right? The sum of the first 300 natural numbers is just going to be 300 times 300 plus 1 divided by 2, right? It's that simple. So it's 300 times 301 over 2. If you like, you can cancel off a 2 and call it 150 times 301. Whatever, you're going to get the same thing. So what is this? 150 times 301 is 45,150. Right? So you're able to get that sum almost instantaneously. So it's a really nice formula. It's a really cool thing. There are other formulas, like you could talk about the sum of the first n perfect squares, or the sum of the first n perfect cubes, or whatever else, right? And there are formulas for all of these things that you'll talk about in calculus, but this is the idea there, and we're going to use this formula for sure in the next section. Okay. Now, one last example that I want to go over, and this is to sort of wet your whistle a little bit when it comes to how these summations are used in calculus. So here's a very calculus-like idea. This is the idea behind integration. The idea behind integration is that we want to know what the area underneath a curve is. And to find that area, we approximate it. At first, we approximate it by drawing rectangles and then computing the areas of these rectangles, right? And adding them up. So let's do that here. So this is the function f of x equals x squared, right? Part A asks, what is the width of each rectangle, assuming that they're all the same width? Let's answer that question. So it looks like we've broken up the interval between 1 and 2 into 4 equal rectangles. That means each of these rectangles should have a width of 1/4. Okay, so that was easy enough. Part B asks, what is the height of each rectangle? Well, the height of this rectangle is the function value whenever x equals 1, right? So it's whatever this output value is, whatever this function value is. So if I plug in 1 to x squared, I get 1. So the height of the first rectangle is 1. I'm going to call that maybe h1 is 1. What about the height of the second rectangle? The height of the second rectangle should be the function value when x is whatever this number is. Now we decided that the width of the rectangle was 1/4, so this should be 5/4, right? So h2 is going to be the function value whenever x equals 5/4. Well, 5/4 squared is 25/16. So h2 is 25/16. h3. So this should be 6/4. Or if you like, you can call it 3/2. So the height of the rectangle is going to be the function value whenever x is equal to 3/2, right? So what is it? Well, 3/2 squared is 9/4, right? So the height of the third rectangle is 9/4. And finally, the height of the fourth rectangle, this should be 7/4. Right? So it's whatever that function value is. Well, the function value is going to be 7/4 squared. So that's 49/16. So h4 is 49/16. Okay. Part C says find x sub k so that f of x sub k is the height of the kth rectangle. Okay, so if I call this one rectangle 1, 2, 3, and 4, right? So for rectangle 1, I want x sub k, so that f of x sub k is the height of the first rectangle. Well, it seems like x1 is just 1. X2 we said was 5/4, but notice that that's the way that we figured that out was we said, well, we're starting at 1 and then we're adding 1/4 to it. So I'm really going to call this 1 plus 1/4. That means that x2 was 1 plus 2/4. X3 oh, sorry, I got my numbering mixed up. So this is x1, x2, x3, and x4. X4 is going to be 1 plus 3/4. Okay, so in general, now going back, notice that I had 3, 2, 1, and then 0. So I'm just going to write in the plus 0/4 for x1. So notice then, in general, x sub k is going to be 1 plus k minus 1 over 4, right? So when k is 1, we get 1 plus 0/4. When k is 2, we get 1 plus 1/4. When k is 3, we get 1 plus 3 minus 1 is 2, 2/4, right? And when k is 4, we get 1 plus 4 minus 1 is 3/4. Okay, so there we go. So there's x sub k. It's 1 plus k minus 1 over 4. If you want, you could, I guess, get common denominators and call this 4 over 4 plus k minus 1 over 4, and that's going to be, of course, k plus 3 over 4. So that's another way that you could write it down. You could just call it k plus 3 over 4. Okay, part D. Part D says, use summation notation to write down the total area of all the rectangles, then find the sum. So the area of the rectangles is going to be the width times the height. So the area of one rectangle, the width of all the rectangles is 1/4, right? And then the height of the rectangle is f of xk. And we just figured out what x sub k is. So the width of each rectangle is 1/4. The height of each rectangle is f of xk. That's f of 1 plus k minus 1 over 4. So the area of each rectangle, right? The area is going to be width times height. Oh, we know what f is, though. F is just x squared. So in other words, this is 1/4 times 1 plus k minus 1 over 4 squared. So there's the area of each individual rectangle. So the total area is going to be the sum from k equals 1 to 4, right? I want to add the areas of the 4 rectangles. K equals 1 to 4 of 1/4 times 1 plus k minus 1 over 4 squared. Okay, so there's the summation notation for the total area. Now, if we want to figure out what that is, we just start plugging in numbers for k, right? We would say this is 1/4 times 1 plus, when k is 1, we get 0 over 4, plus 1/4 times 1 plus when k is 2, we get 1/4. 1 plus when k is 3, we get 2/4, which is the same as 1/2, whatever. And then when we plug in 4, we get 1/4 times 1 plus 3/4 squared. So I'm running out of room, but what would we get here? We would get 1 squared is 1, 1 times 1/4 is 1/4, plus 1 plus 1/4 is 5/4. 5/4 squared is 25/16, and 25/16 times 1/4 is 25/64. Here we would get 3 halves. 3 halves squared is 9/4. 9/4 times 1/4 is 9/16. And then here we would get 7/4. 7/4 squared is 49/16 times 1/4 is 49/64. And let's see how much that is. 1/4 plus 25/64 plus 9/16 plus 49/64 is 63/32, right? 63/32. That's the area there. Okay, so you'll be doing this kind of stuff when you get to integration in calculus. So that'll happen towards the end of your first semester of calculus, as you're going to be looking at stuff like this quite a bit. And it's going to get even a little bit more complicated than this, but that kind of scratches the surface of it, so that at least you're not completely blindsided when you start to do these things. Now, something really interesting that you're also going to look at in calculus, but you probably won't look at this until your second semester of calculus, is the idea of adding up infinitely many terms. So, so let's say that you wanted to add up all of the terms of a sequence, right? So you wanted to perform an infinite summation. These kinds of sums are called series, right? And like I said, you'll talk about these a lot in calculus. You may wonder, well, what is there to study? Isn't an infinite sum going to always be infinite? Like if you add an infinite number of numbers, aren't you always going to get infinity? And the answer, surprisingly, is no. Sometimes you can add, well, sometimes you do just get infinity, but sometimes you can add an infinite number of numbers and get a finite number out of it, right? And you'll spend a lot of time in calculus deciding when that happens, okay? In your second semester of calculus, you'll spend maybe a third of the semester talking about that. So, so if you're interested in this, you should take a look at these two videos. It's really interesting. It kind of has to do with the concept of if you walk halfway from where you are right now to the nearest wall, and then you walk halfway from that point to the wall, and then halfway from that point to the wall, and then halfway from that point to the wall, you could do that forever, theoretically, and you would never quite reach the wall. But assuming that you had an infinite amount of time, then you would eventually hit the wall, but you wouldn't ever go any further than that, right? So it's related to that kind of idea. Take a look at these two videos. I think they're really interesting. That's all I have to say about this, and so we'll see you in the next section.